Greetings, I am Professor Kartikeya Bolar. Let's explore our research on segmenting religious tourists using machine learning.
When analyzing visitors to major religious sites, the tourism industry has historically relied on a convenient assumption, the monolithic pilgrim. But human intent is rarely that uniform. The reality of crowd movement is chaotic, localized, and highly varied. To study these demographics, market researchers typically deploy standardized surveys. The flaw with this method is structural. Surveys force respondents into predefined, biased checkboxes, restricting their answers to whatever the researcher already decided was important to ask. Social media analytics provides a rigorous alternative. Unstructured, user-generated spatial data, like the free-form text found in online map reviews, captures genuine, unprompted human motives exactly as the visitor experienced them. This map details the geographic context surrounding the Golden Temple in Amritsar. As one of the most visited shrines in the world, it generates thousands of highly specific, localized text reviews on platforms like Google Maps. Processing this volume of unprompted text requires a different approach than the traditional survey, one built on the application of unsupervised machine learning. In their recent study, researchers Puramanayagam, Malia, and Bolar established a specific framework for isolating behavioral segments from these raw digital footprints. Their objective is to transform thousands of messy, structurally varied text reviews into mathematically validated demographic profiles. To accomplish this, they utilize a strict sequential analytical pipeline, beginning with text preprocessing, moving into latent semantic analysis, and concluding with agglomerative hierarchical clustering. This pipeline allows analysts to map hidden market heterogeneity and extract deep behavioral insights without ever asking a user a single survey question. This workflow architecture in the Orange data mining environment illustrates the complete technical journey, moving from raw corpus extraction on the left to verified cluster output on the right. The first computational step is text preprocessing. The software systematically scrubs the dataset, stripping out punctuation, URLs, and common stop words that add statistical noise without providing any actual meaning. The clean text then undergoes bag-of-words vectorization. The algorithm dissolves entire documents into a grid matrix, converting individual words into strict numerical frequency counts across rows and columns. This word cloud visualizes the immediate high-frequency output of that vectorization, mapping the most dominant raw terms found across the entire dataset of 250 reviews. But raw word matrices possess a critical vulnerability: extreme data sparsity. Because most specific words only appear in a handful of reviews, the vast majority of the resulting matrix consists of empty zeros. Furthermore, natural language relies heavily on synonyms and polysemy, words with multiple meanings. This creates false divergence in the vector space. The algorithm sees two different words and assumes two entirely different topics, even if the users meant the exact same thing. Raw word frequency alone fails to capture the underlying semantic intent of the user. To proceed, we must mathematically reduce the dimensions of the data. Latent semantic analysis, or LSA, serves as the mathematical bridge connecting those raw word counts to actual human meaning. LSA applies singular value decomposition. It takes that massive, highly sparse term document matrix and compresses it down into a dense, lower-dimensional semantic space. This reduction forces mathematically similar words, the synonyms that previously confused the algorithm, to merge into singular, latent thematic nodes. The result is highly structured data. Here, an unstructured paragraph evaluating the Golden Temple's history and architecture has been successfully processed and mathematically tied to a distinct thematic group, labeled Cluster C1. LSA successfully translates chaotic human language into pure mathematical concepts. This yields the pristine data structure required for accurate, large-scale clustering. With the text converted into refined topic vectors, the next challenge is sorting these vectors into objective demographic groups without introducing human bias. Researchers utilized agglomerative hierarchical clustering. Every single review starts isolated, iteratively merging with its closest statistical neighbor until distinct demographic branches emerge. This contrasts with k-means clustering, which forces analysts to guess the exact number of segments up front, a flaw when exploring unknown niches. However, measuring the distance between text elements presents a specific problem: document length variance. A one-sentence review and a 5-paragraph essay carry vastly different footprints. Standard Euclidean distance fails here. It mathematically penalizes long documents compared to short ones, placing them far apart in the vector space, even if they discuss the exact same topic. To solve this, the pipeline applies cosine similarity, establishing a scale-invariant metric. Rather than measuring the absolute distance between endpoints, cosine similarity measures the angle between two vectors in space. It entirely ignores the magnitude, or length, of those vectors. By combining hierarchical clustering with cosine similarity, the algorithm isolates the exact meaning of the text. It renders the analysis completely blind to review length and immune to human assumptions. Unsupervised machine learning carries an inherent risk. Algorithms will sometimes cluster random statistical noise into meaningless groups. To counter this, the researchers deployed a strict validation protocol. They took the newly generated clusters and treated them as dependent variables, testing them against supervised machine learning models. Ensemble techniques, specifically random forest and AdaBoost, checked the validity of the clusters. These algorithms cross-validated the groupings, achieving predictive accuracy rates between 75 and 94%. Passing this validation phase confirms the algorithm did not invent statistical artifacts. It mapped verifiable structural truths about the tourist population. This perceptual map visualizes the ultimate output of the pipeline. The text data is plotted in two-dimensional space, revealing a clear separation. The algorithm isolated 3 distinct clusters, coded here in red, blue, and green, proving visitors are heavily segmented by their distinct motivations. This mathematical output provides a contrast to the industry assumption of the monolithic pilgrim, revealing a reality defined by significant segmentation. Decoding the LSA topics reveals who these segments actually are. Cluster 1 consists of heritage explorers, tourists driven strictly by historical facts, architecture, and cultural significance. Cluster 2 identifies the aesthetes. These visitors focus heavily on the physical environment, emphasizing sensory experiences and visual beauty in their reviews. Finally, Cluster 3 isolates self-transcendent seekers. This demographic focuses inward on spiritual growth, serenity, and participation in religious rituals. For destination management organizations, the operational implications are massive. A single physical site serves entirely different psychological functions for different user matrices, requiring vastly different services, messaging, and infrastructure. By layering natural language processing over scale-invariant clustering, analysts can bypass survey bias and extract the truth of human intent directly from chaotic spatial data.